Hey, welcome to my channel. So this is the first official lesson of Laplace transforms. So we talked about it last time in the previous video, and so now we're going to talk about it actually implementing a Laplace transform this time. This covers part of what's in section 7.2 of Nagle, Saff, and Snider in their differential equations book. You'll notice I am watching my children today, and so I have hid away in their little house. And hopefully it'll give me enough time to record this video. Anyway, so what you'll notice is that we're going to be talking about indefinite integrals. And these are integrals that go from 0 to infinity. Which means that we're going to be taking limits. More than that, if you look at the form of the Laplace transform, it's always going to be a function times an exponential, a decaying exponential. And so what that tells us is that we're going to be using integration by parts a lot. So for instance, we'll have polynomials times an exponential, which means that you're going to set u is equal to, say, t to the n, and keep iterating it, say, n times until the t to the n disappears. We'll have a whole table by the end of it, so we're not going to do that every time, and I probably won't do that more than just say t squared for the examples in the class. And then we're also going to be considering things like exponentials, Laplace transforms of exponentials, and Laplace transforms of sine and cosine. And when we involve sine and cosine, what that's going to bring back are the concepts of solving for the integral. And so there we're going to use integration by parts once or twice, and then we're going to find our integral again that we want to solve for, and then we just treat it like an algebraic equation. So again, we're not going to do this every time. We're going to develop a table of doing it, but in order to make this table, we have to go through some painful steps first. You will probably be expected to do at least some of this stuff on the exam, so just make sure you review how to do integration by parts and a few other things like that, and you should be good. Anyway, so later when my children are taking their nap, I'm going to go ahead and record the lecture using alright, getting into boxes. So I'll record a lecture later while my children are taking a nap, and so you'll see that right now. Okay, so let's get this done. Alright, so we're talking about section 7.2, and this is in Nagle, Saff, and Snider's book. Alright, so to start off, we should talk about what the definition of the Laplace transform is. There's two ways we write it. Typically, what we do is we start off with a function f of t, and so this is a function that's defined, so say with domain, say 0 to infinity. And the Fourier transform, not the Fourier transform, the Laplace transform for this function, we will often denote by cursive L of f of s, and sometimes we'll also write this as just capital F of s when we want to have a shorthand. So now this is defined as the integral from 0 to infinity of f of t e to the minus st dt. Okay, and so what we see immediately is that this is a indefinite integral. So we are integrating from 0 to infinity, and we're multiplying by e to the minus st, which tells us from all of our experience doing integrals in calculus 2 is that we'll probably end up using integration by parts. Okay, so one thing we need to say is that, so what we say is that L of f is the Laplace transform of little f, and we say this is whenever the integral on the right exists. So remember back in, say, calculus 2, we worried a lot about whether or not we had infinite series converging or if indefinite integrals converging, and it's the same sort of deal here. And so a lot of times what we're going to be wanting is we're going to want to make sure that this is sort of dominated by a decaying exponential. And later on, when we get into the second video for section 7.2, we'll talk about what it means to be of exponential order. And this is one way that we can guarantee the existence of a this is one way we can guarantee the existence of a Laplace transform. Okay, so other key features to notice is that this is a function of t, and now the Laplace transform is a function of s. So we've switched from a time domain, so we'll say t is the time domain, and we're switching to s, which is the frequency domain. Like I said before, the frequency domain thing is coming from the Fourier transform, which is used a lot in signal processing. And so that's what we have here. Okay, so this is the Laplace transform of a function. And let me think, is there anything else I want to say at the moment? No, I think what's good now is if we just get into a couple of examples. So, in generally speaking, what we're going to be wanting to do is we're going to be wanting to jump from little f to big F of t and then of s respectively, and we're going to be switching from problems in calculus to problems in algebra. And so we're going to have a lookup table that we're trying to build up. So I'm going to talk about three functions here that we're going to try to go over. And then that will give us the beginning bits of our table, and then we can talk about it more. So we're going to talk about three functions. We're going to talk about the function f of t, which is equal to 1 for all t bigger than or equal to 0. We're going to talk about another function, which is e to the at for all t bigger than or equal to 0. And then we're going to have f of t being equal to sine of bt for all t bigger than or equal to 0. Okay, so these are the three functions we're going to talk about, and this will allow us to start building our table. All right, so let's do that. All right, so for the first one, just a second. Cat jumping on the table. All right, so the first thing we're going to look at, the first example is f of t being equal to just 1. All right, now remember, we're going to be concerned with whether or not we have a convergent integral. So I'm just going to leave, so I'm going to say the domain of Laplace transform up here, and we'll figure out what that has to be as we go. All right, so for the function that is just identically 1, we just go ahead and throw it into the definition. So capital F of s then is going to be equal to the integral from 0 to infinity of 1 times e to the confusing things, times e to the minus st dt. Okay, now this is pretty straightforward. All right, first thing to do, remember with indefinite integrals, we need to switch them back to limit. Limit as, say, capital N goes to infinity. We have the integral from 0 to n of e to the minus st dt. All right, now we figure out the definite integral on the inside. And so this is the limit as n goes to infinity of e to the minus st divided by minus s, and we're evaluating this at 0 and n. Okay. So let's keep it going. All right, so we're still taking a limit as n goes to infinity. Don't forget to put that. And now we're going to have e to the minus sn divided by minus s. Then we're subtracting e to the minus s0 over minus s. Okay, so this second chunk here, this is just going to be 1 over minus s. And this piece is e to the minus sn. Well, provided if s is positive, then minus sn is negative, so this goes to 0. Right? So what does that leave us with? Well, it leaves us with minus 1 over minus s, or just 1 over s. Okay, so now we've finished that, and we figured out what our domain has to be. So we need s to be bigger than 0, right? Because we want to make sure that the integral itself converges, which means that this limit has to go to 0, or at least converge. Okay, so what do we find? We found a Laplace transform of the function 1 of s is equal to 1 over s, right? And this is what we're also denoting as capital F of s. Okay, so now let's take a look at the next one. All right, now we're going to take a look at the second example, which is where we have f of t is equal to e to the at, right? Now I'm going to again leave a domain of Laplace transform here, so we can get back to that in a minute. And let's go ahead and work out this integral. All right, so the integral itself is coming from taking Laplace transform. This time I'll use this notation of s, Laplace transform of e to the at evaluated at s. And so this is the integral from 0 to infinity of e to the at times e to the minus st dt. All right, combining things, and let's go ahead and throw a limit in. So limit as n goes to infinity of the integral from 0 to n of e to the a minus st dt. Okay, now just go ahead and do the integral. Pretty much the same thing we had before. So it's the limit as n goes to infinity of this guy. So we have e to the a minus st divided by a minus s minus e to the a minus s at 0 divided by a minus s, and that was a t over there. That's supposed to be capital N, so I'll replace that. Okay, now again, what do we need? Well, we need basically that a minus s has to be negative, because we want this thing to go to 0. All right, so if that's negative, then that means that s has to be bigger than a. All right, and so that gives us our domain. A has to be bigger than s. All right, now provided that happens, then that means that a minus s is less than 0, which means that that term goes to 0, and what we're left with is we're left with minus 1 divided by a minus s. That's because e to the a minus s times 0 is 1. All right, so just rearranging things to make things look pretty. We have the Laplace transform of e to the at is equal to 1 over s minus a. Right? And so let's write that nice and big. Laplace transform of e to the at evaluated at s is equal to 1 over s minus a. Okay, cool. All right, so now we have two Laplace transforms that we worked out. We have one Laplace transform with a constant function 1, and that gave us 1 over s. Now we have a Laplace transform of e to the at, which gives us 1 over s minus a. The reason why these things look so similar is really two reasons. One thing that we know is that 1 can actually be written as e to the 0t, right? And so that would be like having a being 0, and that would match up right there, where we have s minus 0, right? Another thing, and this is a big property we're going to develop later, is that when you multiply a function by e to the at, then you'll actually end up shifting the Laplace transform. So another way to look at this is that this could be thought of as e to the at times 1, and then we're just shifting the Laplace transform of 1 by a, and that gives us that. These properties you'll get used to using later, and that'll be the subject of 7.3. But right now, we'll just leave it at the raw things that we've calculated so far. Okay, so now for the third one, let's go ahead and take a look at the Laplace transform of f of t equals sine of bt. There's actually two ways to get at this. One thing we could do is we can actually rewrite this as e to the I bt minus e to the I minus I bt divided by 2I, and that's Euler's formula that we saw before. And then we can just apply the Laplace transform separately to each of these guys and put it all back together later. But the more direct route to do it is the good old calculus 2 way, and that's where we end up solving for the integral. So here, let's just use capital F notation. It's going to give us integral from 0 to infinity of sine of bt times e to the minus st dt. And again, we're going to be concerned with the domain of the Laplace transform. And we'll talk about that later. So basically what we're going to do is we're going to declare this whole chunk as I. This is the integral from 0 to infinity, and so we're calling this integral I. And what we're going to do is we're going to try to work it down to a form where we can have I on both sides of an equation and then just solve for it. And so let's go ahead and do that. And this is going to involve u substitution. So here, what I'm going to do is I'm going to take u is equal to sine of bt, and I'm going to take dv to be e to the minus st dt. Right? That gives me du is b cosine of bt, and that gives me v is going to be e to the minus st divided by minus s. All right, so plugging all that in, so I'm going to have sine of bt. Let's first put our limit. So limit as n goes to infinity, all right? And so it's going to give me sine of bt times e to the minus st divided by minus s. Then we're going to subtract v du. So that's going to be minus, and then since we have this negative sign here, we're going to put a plus sign here. Integral from 0 to n of, say, b cosine of bt e to the minus st, and then we're dividing by s, right? Okay. This is dt, and this over here needs to be valued at 0 to n, right? Okay. So I can go ahead and I can keep working on this, but I want to clean things up a little bit. So let's take a look at what we get here. So this itself expands into, say, sine of bn times e to the minus sn divided by minus s. And then we're subtracting, sine of 0 is 0, and so this gives me 0. Okay. Now, sine is bounded by 1, and so we can use a comparison test against e to the minus sn. And so if e to the minus sn ends up going to 0, then the squeeze theorem tells us that this whole chunk goes to 0. And for that to happen, I need s to be bigger than 0, and that actually would be enough for us. So, then this term, as n goes to infinity with this domain, gives us this going to 0. Okay? All right. So that means that this whole piece here is 0. Okay. So now let's take this guy and restart it over here. All right. And now we have that first chunk gone. And so we have limit as n goes to infinity. And we have, say, b over s, integral from 0 to n of cosine of bt e to the minus st dt. Okay. Now again, we need to use integration by parts, so let's go ahead and do that. So we have u is equal to cosine of bt. We have du is equal to b sine of bt, and my sine coming out there. And then we have dv is going to be e to the minus st dt, and again that gives us v is equal to e to the minus st divided by minus s. Okay, so what do we get? So it's going to be the limit as n goes to infinity of b over s, and then we have all of this stuff. So we have u cosine of bt times e to the minus st divided by minus s minus the integral of v du. All right, so we actually have two minus signs, one coming from du and one coming from v, so we'll keep that minus there. And See, we're going to kick out another b, and we're going to kick out another s. We have the interval from 0 to n of sine of bt e to the minus t dt. Okay, and now let's get rid of this limit. We have to integrate this piece 0 to n. All right, so let's go ahead and do that. So limit as n goes to infinity of b over s. This term here is going to be cosine of bn e to the minus sn divided by minus s. Then we subtract off whatever we get when we put in 0, which is going to be 1 over minus s. Then we have minus b over s integral from 0 to n of sine of bt e to the minus st dt. Okay, all right, so what do we get? All right, so this piece, just like we said before, is going to 0 because e to the minus n is going to, e to the minus sn is going to 0 as n goes to infinity. And since cosine is bounded by 1 in absolute value, that means that we can use the squeeze theorem to say that's going to 0. Okay, and so that leaves us a couple more little pieces. And now I'm just going to go ahead and expand out the limit. So I get b over s times 1 over s minus b over s times the integral from 0 to infinity of sine of bt e to the minus st dt. And if I multiply through by bs, I get this. I get b over s squared minus b squared over s squared, and then times the integral from 0 to infinity of sine of bt e to the minus st dt. And so again, this is what we're looking for. This was our I. So if you look at the very left-hand side of everything we did, that is I there, and then we have an I popping up over here. So let's go ahead and take it to the onto the next page. So we have essentially I is equal to b over s squared minus b squared over s squared I. And let me just double check before I run with that. Yes, that's what we got. Okay, so now let's just solve for I. Okay, so this tells us that we get 1 plus b over s squared times I, moving this guy over to the left. And this is equal to b over s squared. Okay, now what do we get? Well, I can go ahead and divide by 1 over b, 1 plus b over s squared, and that'll give me I. So this tells me that I, which is actually equal to the integral from 0 to infinity of sine of bt e to the minus st dt, is actually equal to b over s squared times 1 over 1 plus b over s squared, and this should have been b squared over s squared, so correct that real quick. And now if I multiply numerators and denominators, I get b over s squared plus b squared, right? And that, my friends, is the Laplace transform of sine of bt evaluated at s, right? And so that's what we got. So we've done 3 examples of Laplace transforms. We did Laplace transform of just the constant function 1, which gave us 1 over s. Then we did a Laplace transform of e to the at, which gave us 1 over s minus a. And we saw that this could actually be thought of as shifting the last one. And over here, we have sine of bt. We took the Laplace transform. We could have done it like this, and this would be a really good exercise if you wanted to see how well you do with complex numbers. And otherwise, we used the integration by parts method, and we got b over s squared plus b squared. Okay, so this is the beginnings of our table, and it's actually most of all we need for our table. We have these 3 functions, and then we can build up everything else by using the special properties that we'll develop in the next section. So we'll have techniques of finding derivatives of, finding Laplace transforms of derivatives of functions, and then later on we'll go on and find shifting properties, multiplication by t, and all this other stuff, and that'll be enough to actually build up the entire table from really just these 3 examples. So With that, I guess we'll take it back to the child's playhouse. All right, bye. Okay, so that was the Laplace transform. So that's the definition, and we went over a couple of examples. So I'll make another video where we go through a few more examples later in the week. And it sounds like I need to get going. All right, bye, and thanks for watching. Hey, buddy, you doing okay? You have a boo-boo? Want to say hi?
No.
Okay, all right. Bye-bye now.